Now we got a metallic electric wire of diameter d 5 millimeter is to be coated with an insulation of thermal conductivity. So thermal conductivity constant is given K, which is 0.35 watt per meter Kelvin. It is expected that for a typical installation, the coated wire will be exposed to a condition for which the total coefficient associated with the convection and radiation. So we got a coefficient for convection and radiation as 15 watts per meter square. We want to minimize the temperature rise of the wire due to the ohmic heating, because when the current will pass, it will heat. The insulation thickness is specific so that the critical insulation radius is achieved. Okay, so we are looking for critical insulation radius. Okay, during the wire coating process, however, the insulation thickness sometimes varies around the periphery of the wire, resulting in eccentricity of the wire relative to the coating. Determine the change in the thermal resistance of the insulation due to eccentricity, that is 50% of the critical insulation thickness. So how are we going to proceed with this numerical? We got wire diameter, this is how it should be, but obviously we got critical thickness by 2, that's going to be here. We got wire diameter, we know convection condition, we know its insulation thermal conductivity. We need to find the thermal resistance of the wire coating associated with peripheral variation in coating thickness. So this is concentric, this is eccentric wire. And obviously the convection and radiation is happening on this side. Now we need to make assumption steady state condition applies, and we make assumption that 2-dimensional conduction happening, not 3-dimension. We want to assume the steady state properties apply, constant properties throughout the material. Both the exterior and the interior surface of the coating are of the uniform temperature. Now, first thing is we need to know this formula. This is the formula for the critical radius, which is K over H. We got the K, we got the H, and this will be in meters. Yeah. If you want to find the critical thickness has a formula RC minus D over 2. We got the RC from here, 23 millimeter, minus diameter, which was 5 millimeter, 0.005 over 2. That will give you the critical insulation. Now the thermal resistance of the coating is given by this equation. So that's another equation. It's ln bracket RCR, which is radius critical, divided by the radius. So we got the critical radius as 0.023 meters. Everything is going to be in meters. If you want, you can have put the things in millimeters, same answer. Divided by the radius, 0.005 meter per divided by 2, because we have to half it. Divided by 2 pi k. 2 pi, the k is 0.35. Put that value and you will get 1 meter Kelvin per watt. Now for the eccentricity, the thermal resistance of the insulation may be used by using a K7. Yeah, so we have to go for K7, which we already know. The eccentricity Z is given by 0.5 times the T critical. So we have the T critical value, we got this answer. K7, this is the formula for the K7. In some calculator, there is a function called hyperbolic. Yeah, in some calculator you have to go option and then, so you need to go hyperbolic. So remember, this is over here, it's a hyperbolic identity, it's not that one. And then you put the value, the diameter, we got the radius, so 2 times the radius is the diameter, and then you got the diameter, which is 0.05, 4 times the Z, so we got that value, divide by the 2, divide by the D, which the big D, divide by the small one, which is 0.005. I suggest you calculate this top value first. When you do the top value first, you will get an answer. Whatever answer you get, write it down here. So it will be around 2. Yeah, you got the answer. Whatever answer you get, you write the answer here. And then you do 2 pi 0.35. And that will give you the value 0.91. The thermal resistance of the insulation is 0.1. The reduction of the insulation is around 10%. There is a 10% reduction in the insulation. Now, based on that one, we can make some comments. Reduction in the local insulation thickness leads to smaller local thermal resistance of the insulation. And conversely, location associated with thicker coating have increased thermal resistance. Thermal resistance will increase as we increase the thickness. The effect offset each other, but not exactly. The maximum resistance is associated with concentric wire case. For this application, eccentricity of the wire relative to the coating provides enhanced thermal performance relative to eccentric wire case. Now, the interior surface of the coating will be at nearly uniform temperature if the thermal conductivity of the wire is high relative to that of insulation. Such is the case of the metallic wire. But the exterior surface temperature of the coating will not be perfectly uniform due to the variation in local insulation thickness.